There are two sessions today, and one by me and one by our gentleman here from University of Florida. So we will, what we will do is, I will speak for 30 minutes, and then the colleagues from Florida University and Texas, they'll speak 20 minutes each, and then we have about 20 minutes for question and answers at the end. So what I'll speak about is global croplands for food and water security in the 21st century. So using Earth observation data, machine learning and cloud computing. So my colleague Partha Teluguntla is here, who actually did almost all the heavy lifting in computing. It requires massive amounts of computing, especially look at Landsat data, 30-meter resolution, and doing it for the entire world. Anyway, so here is global croplands, and global croplands, I'll give you some brief what you call background before I get into nuts and bolts and details about global croplands. Global croplands is tied up to everything, availability of land and water. With the increase in population, of course, there is a lot of virtual water and virtual food trade that's going on around the world. It is tightly related to climate change. Croplands are not only related to feeding humans, but also animals. Now with the increasing, especially the development of the so-called economically developing countries, the nutritional needs of the people are also increasing. And as you know, food is really peace as well. You know, if you have enough food, people can be peaceful. And this is an interesting slide that I want to see, this just a 1 minute, how the population has progressed in over last 12,000 years. You know, Mexico and Brazil were the biggest population in the beginning of, about 10,000 years back. And slowly China and India started coming, especially 7,000 years back. And ever since then, those are the two dominating countries in terms of population. So much so, there were millenniums, thousands of years where population of the two countries put together was more than the population of rest of the world. So you can see how it plays around. Still about 3,000 years back, India, China, Mexico, Brazil, and slowly some of the European countries coming up. So it's really an interesting thing, and this is so tightly tied up to food security in terms of cropland, water use, and economy, and all sorts of things. So, so if you look here now, especially in the last 2,000 years, the population in India and China has been massive compared to, now Mexico was there, Brazil was there. Mexico, Brazil as well for a long time have been large populations relatively. Now so you can see, and when around 7,500 China becomes the dominant and India's population goes down mainly due to colonization and all the problems associated with this. And as you know, just the UN just announced now India has actually overtaken China to be the #1 country in population. So this is kind of an interesting slide, and then that is related to all the global croplands. So about 3000 BC, there was just 36 million hectares of croplands. 1000 BC, 84 million hectares of cropland, and even at 1900 AD, they were 840 million hectares. And for last 19th century and 21st century, massive expansion of croplands have taken place, which is all, especially from after the Second World War, the population and also cropland increase has been massive. So what is the current state of art in global croplands? You can see all this. I'm not going to read through all this, but there are number of coarse resolution products, which is basically anywhere between 250 meter resolution, that is telling that 1 pixel is 6.25 hectares to 10 kilometer resolution. that is 10 kilometer by 10 kilometer resolution, or 1 kilometer by 1 kilometer resolution, which is about 100 hectares. So if you look at the early maps of global cropland, irrigated and rain-fed area looked like this. You know, about 27% irrigated, 73% rain-fed, and you can see here, especially in the magenta color, related to population, India and China dominate. Nearly 60% of global irrigation comes in these two countries, and US, of course, also has quite a bit of irrigation, and of course, the Central Asian countries and some other countries. Now, related to that is the crop water use. When we talk about water use, the dominant use of water comes from agriculture. This statistics doesn't come from remote sensing, this comes from national statistics. So, for example, India uses 685 kilometer cube per year of water. This is the work from Gleek et al. In 2011, but there has been, this can be improved by, you can even create pixel based water use. But just to give you an idea, that is 685 trillion liters followed by 12 zeros. So much water is being used for agriculture. So massive quantities of water being used for agriculture, and that is directly related to how much croplands you have and how much croplands are actually irrigated. The next thing for global food security is crop water productivity. How much you are going to produce for unit of water. For example, here you are taking just wheat crop and just looking at this for different countries of the world, and you can see here, for example, US, China, and mostly the Egypt, that Nile Valley Basin, you have maximum amount of crop water productivity. That is how much you are going to produce for a unit of water in terms of, this also addresses the yield gap that you have in other countries. It's one of the areas where you can really increase food by growing more food per unit of land and per unit of water. Given this background, the topic I am going to speak today is about how to map global croplands. When I say global cropland, multiple products that address food and water security. So here we are using USGS and NASA data, a planet scale, and using 30 meter or better resolution, and using machine learning, cloud computing, and going forward artificial intelligence as well, to bring up fast solutions. And you can rapidly, you know, machine learning, for example, when we started doing this project, it's almost like magical compared to our earlier computing. It's not that we didn't know about machine learning earlier, it is what happened is the computing power came into being, and that really allowed us to compute massive petabyte scale of computing over a very large areas, continents, globe, etc. So when we talk about global cropland, there are various products we can produce. Where are the croplands of the world? Where are the irrigated and rain-fed croplands in the world? How many times in a given pixel do you grow crop? Do you grow it one time annually, 2 times annually, or is it a plantation crop? Or what are the major crops of the world? For example, wheat occupies about 22% of the world. These are the main crops of the world. Nearly 70% of the world's agricultural croplands are occupied by these crops. So mapping all these different crops, as well as from those what I call as a primary products going into secondary products. Like for example, from the primary products, you can say growth stages, where are cropland fallows, and what is the productivity, land productivity, crop productivity, water productivity. And because we have all this data advances, data is like now even planet scale that these cell phone size satellites that are going up there, acquiring data at 3 to 4 meter almost every day for the entire planet. And so we get massive quantities of data in all spectrum, electromagnetic spectrum. That is there, and then we have machine learning, we have cloud computing. All of this has brought in that it doesn't matter which farm, that you can almost get a particular farm anywhere in the world onto cell phone, and the farmer can look at it, and basically he can even look at, you know, what is my nitrogen, what is my biomass, everything. You can look at 10 or hundreds of quantities of that parameters for that particular farm sitting anywhere in the world. That is the real possibility of what is going to happen, is already happening in many ways. Mapping world's cropland. So now I will show two big illustrations of mapping global cropland. One is mapping the entire world's cropland, where are actually croplands located using Landsat 30-meter data. That means every pixel is 0.09 hectares. That is the level of detail at which you are mapping. So the definition is very crucial in mapping. And definition is cropland, that is standing crops, cropland fallows, plantation crops. So that is how we define. Of course, you can define, you can bring in other type of things into the croplands, but our definition basically, whether it is standing crop, even if it is fallow, that is the land that is equipped for cropland, and then plantation crops. And then how do you define irrigation? See, this is a fascinating thing that also may be quite controversial that I am going to speak today, that needs to be thought about, that, you know, the irrigation is expanding far more than what we think is actually happening, and I will give you some reasons for that. So irrigation is, what is irrigation? Artificial supply of water for agriculture. And even if you supply water once during the growing season, we consider that as a irrigation. A rain-fed agriculture is purely rain-fed. That means there is no artificial means of agriculture. Suppose if you go to Sahel, it is purely rain-fed agriculture. So let us look at, these are some of the examples. You know, for example, if you take centripedes in Texas, or river deltas in anywhere, Nile or the Tamil Nadu or wherever, and, you know, like Indus River Basin in Pakistan, or something like that. So these are some of the, these are got from what we call as sub-meter to 5-meter data. Those are also available quite frequently these days, and we can use them as a training for high resolution data for machine learning. So there are some other examples of how irrigated areas look like. So rain-fed areas are purely rain-fed, you know, where you have no artificial supply of water of any kind, no pumping, no deep water, shallow water pumping, or irrigation wells, bifurcation from the rivers, or creating reservoirs, or none of that, those things. You know, some of the examples are Midwestern US, for example, is purely, mostly, you know, rain-fed. And then Niger, for example, if you take especially Sahel and Sudan savannas and Sudan savanna, Northern Guinea savanna, and Sahel, often in Africa, and in large swaths of Australian croplands are all rain-fed. So you, and here are some of the other examples of rain-fed agriculture. So now, so you know that you have data that is, that data is like from various satellites. Landsat is one example that is acquiring data in 11 electromagnetic spectrum in the visible, near infrared, shortwave infrared, thermal infrared, and all that. And of course, you can have, you know, very high spatial resolution data from, like from the planet, which is sub-meter to 5-meter data. And also that also comes in multispectral. And then you can have data from even hyperspectral, that is hundreds of bands of data continuously from, let us say, from 400 to 2500 nanometer and things like that. But once we have that, how do we do really mapping? That is what I want to show you here. So you have hundreds of satellites of data, and then you create analysis ready data. That is, these are actually, you can go to any place in the world and you can create these data cubes from multiple bands of data. And how do you create this? This you can create it on the cloud, like for example, Google Earth Engine, Amazon Web Services, or whatever. So you can create it. The beauty that has happened is, earlier we used to spend all our data. I remember when I was doing my PhD, I had 1/4 scene of Landsat data, and I did my PhD from Ohio State. And I went to my advisor, Dr. Andy Ward, and I said, Andy, I want one more scenes of Landsat, and just one more scene. Then he said, at this rate, Prasad, he thought that I was already doing too much. So he said, at this rate, you'll never get done. So now we do this for the entire world repeatedly so much, and it's mind-boggling, really. So, but this, because of the cloud power that we have, like Google Earth Engine or Amazon Web Services, we can create this cloud by not downloading data, but right in the cloud. So we don't have to download, store, and all that data. So it saves a lot of time and effort. And then you have all these machine learning algorithms, like random forest, support vector machines, and object-oriented, like hierarchical segmentation. I don't have time to go into each one of these, but we have written several papers on all of this, and basically we have worked on all of this. So you can really create either code it, for example, using Python and JavaScript on Google Earth Engine. You can code it and compute it directly using any one of these algorithms. And you can take, for example, I can look at the entire world and do the computing. This is actually a Google Earth Engine platform, and I can take a small area, I can take the whole area of the world, as long as I have the data. And data is also available in the Google Earth Engine. You pull the data, whether it is Sentinel data or Landsat data, whatever data you want, and you compose it and compute it right there. And the next is really the automation in artificial intelligence. I keep telling that at least to my team members, that we should not be doing this again and again every year, but we should basically automate the process. That means that you just put the data, you click a button, you get a result, and that's where we are going, really. And much of the ChatGPT and all this new buzz on the AI that is now happening is becoming really, other day I just asked OpenAI, I went and said, give me a code in random forest, write me a code to classify an image. It actually did a pretty good job of giving me the initial code, and you could start off there. And now this is really the beauty of what has happened to the present world, how much easier it is getting for people to do these kind of things. So you can start off with an object-based classifications and use both supervised and unsupervised classification approaches, or various other type of classification approaches to classify your images. This is a whole, I don't have to go into, as we have shown, we have written a lot of papers on those, and those are all available. At the end, I'll show you where to go, and there is one site you can go, and you can basically get all the information you want. The way we have computed, I'm just looking at the time, sorry. The way we have done is that we have divided the world into 74 agroecological zones. The FAO's global agroecological zones were reduced to 74 agroecological zones, wherein we compute different type of all these products that we compute and then stick them together. Because if you do a computation across the world, the results can be fuzzy at times. And of course, as I mentioned, you can create these data cubes directly in the cloud to get information. And this type of data cubes are created for each one of the agroecological zone, and then you write these codes, and for the machine learning to compute, like whatever, you create, you can say, give me NDVIs of this, and do a classification of this, and all those kind of things that you can do it right there. The other thing that I want to really show is that if you, okay, so that had a video, but that's okay, but I don't have to show that. But basically what this shows is, this is a time-lapse image. That what happens is, if you click anywhere in the world, you can almost see on a daily basis how it is changing. And that is at 1 meter to sub-meter to 5 meter resolution. That is the level of information that is coming from. So you have all these hundreds of satellites up there just for Earth observation. and the planet is just launching, like sometimes put their 50 satellites up there in one of these rockets up there, and they all go and start acquiring data. So we can gather these kind of high level of training data, and we can also go and do ground data collection. Partha actually went to Australia and spent a month just collecting all this data, and that's the best way of getting the data. That way all the details about what it is, whether it is irrigated, what type of crop, and all sorts of things. Nothing like, see, you need all this data for three things. One is for training machine learning algorithms, identifying, labeling the classes, and validation of the products. So for the three things you need this, and just to show. So ultimately, when you get it both from the ground data as well as from these microsatellites that you have, you get all this data, which is, for example, for cropland and no cropland, we acquired over 100,000 data points for across the world, and we used 60% for the training and 40% for the validation. For irrigation, you can see all the data points for irrigation around the world. There's a lot of irrigation in India and China and US, for California, for example, and I'll show Nebraska in a little more detail later. But you can also see all the rain-fed croplands wherever. You see here all the Midwest and Canada rain-fed cropland data points. So these data points are very important. So once we get those data points, we do what we call as training. So we say this is a cropland, this is non-cropland, and those kind of things that we do. And what this does is, these data points over the time series, a particular point might be, there might be mixture between non-cropland and cropland in a particular date, but as the time goes on, this same pixel might go somewhere here, and this might go somewhere here. So with time, because we have temporal data, that becomes helps for separating everything so well. So what happens is, for any given region, you use a random forest, you use object-oriented classification, you synthesize between these two and produce this and compare this with the reference data set. And you can see here, this is a reference data set and this one, and then it looks, and the same thing is done for irrigated and rain-fed. You create a knowledge base wherein you are separating irrigation and rain-fed clearly, and irrigated in the green, and this is red. See, whatever you put into a computer, garbage in, garbage out technology is very much real. So any computation requires, initially when Google Earth people will show something, people will say, but thing is, if you really look at it, there are a lot of inaccuracies. That is because your knowledge is not perfect. So you need to have a knowledge base which is very perfect. You can establish clear separation through some very logical ways of doing this. So for example, this is a very complex process. Partha works very hard on this every day. And for example, if you take Africa, taking irrigated areas, we're doing some, let us say 40 unsupervised classification and reduced to 21. You can see these signatures. These are real signatures telling you, this is like a signature of a story, that for example, this is a single crop, this is a double crop, and this is a single crop with a different season. All sorts of things you get. So you group them, all the similar things you group them and put them together. And then we have what they call a spectral matching technique. So the spectral matching techniques work like this. So you have an ideal spectra that this shows irrigation surface water double crop, that we know because we have done lot of field work and developed a clear signature for a double crop. This is from the Ganges Basin. And when you do a classification, you get all those signatures, and what you do is you try to see which of the classes matches with this, and then you say, this is the most likely class for this one. It doesn't matter where it is in the planet. So then you say it is a double crop irrigation because it matches, and that is the first level of identification. And then you basically combine all these classes and say this is a green ideal spectra, and then that red class, which is basically the from your classification. Similarly for the single crop that you do. And you have, of course, this what they call as two-dimensional spectral spaces that you have, for example, the red band and the near infrared band. Here, for example, you can see here all the rain-fed classes, irrigated classes in the two-dimensional space. And this one, this is that dates here is a Julian dates, actually how a particular class, a irrigation class goes around with time in a given year. Rain-fed class, how it goes around in a given year, and this is the soil line. And this is actually a forest, you know, like this is always here. So there is always this spectral signature coming from various electromagnetic spectrum that you gather. So finally, based on all this analysis, Africa has 49.5 million hectares of irrigation. And what are those type of, we can be very detailed in classifying what irrigation is. Irrigation coming from, this is from an irrigation mask, and it's a double crop, mostly based in Nile Basin, 2.7% of this 45 million hectares. So anyway, this is too much of a detail for to discuss here, at least in this discussion. And then similarly for rain-fed, you can see here Africa dominant rain-fed mostly, and rain-fed single crop 18.1%. And you know, so you can actually color code each one of them separately. He has a real clear signature and can label them very well. And you can combine them and say, show me all the irrigated areas from the 49.5 million hectares, and how much is single crop, double crop, continuous crop. Continuous crop is mostly plantation. Of the Africa's 263 million hectares of rain-fed agriculture, how that is distributed, nearly 60% is single crop, and you know where single crop is, and so on. And finally, you combine both those two, irrigated and rain-fed masks, and combine and produce an Africa-based map for that. So going into this is croplands of Africa. Just you know, just cropland and no cropland. And then this is irrigated versus no rain-fed. So in Africa, you can see here only 15% is irrigated, 84% is rain-fed. There is a tremendous potential for Africa to increase food security just by increasing the irrigated areas. And this is US, you know, cropland and no cropland. And you can see here where are all the croplands distributed in US. And rain-fed and irrigated in US, you can see here. You know, California, for example, Nebraska here, and Mississippi Valley in these states, Arkansas, and you know, so and you can see here where it is all distributed. So for the globe, because I showed those 74 zones, you can do it for each continent or each region and stick them together, and then produce this beautiful map of where is cropland and no cropland. Nearly 13% of the terrestrial area of the world is cropland, which is about 1.8 billion hectares of cropland. And irrigated and rain-fed, I think it's about 39%, and you know, 61% cropland. And you can do this because it's a 30-meter data. You can do it in great detail and produce it for every county, how much is cropland. So you can generate county-wise statistics. I would say even village-wise statistics of cropland and no cropland. For example, this is, we are right here in Lincoln, and you can see here all irrigated areas. In fact, Nebraska and California are the two leading irrigated areas of United States in terms of states. Of course, this is California's irrigated area, mostly in the Central Valley. Nearly 85% of all California Central Valley is irrigated. So accuracies is very important to know. So I'll take 5 more minutes, maybe less for questions, sorry. So you can see here, what happens is for each one of the zones, you can get accuracies. For example, if you take this zone, what it says is 85% we have mapped it correctly. That is, we have captured where the croplands are, and we have missed about 12%, you know, that is omissions. And sorry, this is omissions, and this is commissions. That means the 88% is user accuracy. The commission errors is about 12%. So this can be done for accuracies. We call it error matrix. This can be done for everywhere. And to do accuracies for irrigated areas of the world, we have this independent data set for the entire irrigated areas of the world, and we mapped irrigated areas with a producer accuracy of 86% user accuracy. That means we actually missed about 14% of irrigated areas, and about 16% of non-irrigated areas came into irrigated areas. That is quite inevitable, to have this errors of omissions and commissions in this kind of work, especially when you are doing global areas. Of course, there are multiple uses of this map. You can create these kind of beautiful maps to show, for example, India has about 180 million hectares of cropland, which is about nearly 10% of the global cropland area. And usually I call it South Asia and Europe as the agricultural capitals of the world, because Europe, even though everybody thinks as industrial countries, most of France, Italy, Germany, all of them have more than 50 to 60% of their geographic area under cropland, whereas US is about 18% because it's a large area. So that's something to note about. And how irrigated areas are distributed, you can see here India, China, US, leading countries, and how rain-fed areas are distributed. And you can see here US and Russia, for example, leading rain-fed countries, Brazil as well. And you can produce these kind of beautiful maps of the counties, for example, county-wise irrigated areas, and you can see all the green areas where, and of course, this is the highest irrigated areas, California, Nebraska, Mississippi Valley, and you can see all the different, this one, and the rain-fed areas where they are concentrated, you can see mostly in the Midwest, and also, and again, here this is county-wise cropland area as a total. So in terms of impact, our work is nearly used by 126 countries. This data is released through NASA's LPDAC, that is a gateway to release all land-related data. So anybody can download our data from LPDAC. In 2022, 72 countries, 2021, 96 countries used our data. So I have a whole, we have a whole monograph that is written. You can download it using this link. And if you go to our site, you can basically get maybe about at least 15 papers from that you can download that on these methods. Dissemination, this website is the key that will lead to everything else. I would suggest, if you want to look at our products in great detail, go to croplands.org, very simple address, and you can browse into any place in the world and zoom in and see for yourself all the details of our product, multiple products. And this is NASA gateway of our data. So these are released and they can be downloaded here. This is rain-fed and irrigated. This is cropland and all that. Thank you very much. Yeah, I took 35 minutes and my colleagues have 20 minutes talk. So do you think that I should just take 5 minutes question? Yeah, 5 minutes of questions maybe if you have, and then maybe we can go to them. Yeah, go ahead.
I have a question about training. The data that's used to train AI models is compiled, as you described, by USGS, presumably. But who actually runs the training operation? Does USGS do that, or does OpenAI do that? Do you give them data? How's that work?
No, in this one we do it ourselves. So we collect this data for the particular purpose. See, there can be for a different objective. For example, if you are collecting data only for cropland, no cropland, you can only use for that. Irrigation, no irrigation. So we know exact purpose. So we spend lot of time in collecting this quality data. The one key thing about data is that it is not the quantity, it's the quality of the samples. The quantity is, numbers doesn't matter. If you have 100 samples that are, you are 100% sure, rather than 150 samples or 200 samples where you have uncertainty. So uncertainty leads to uncertainty, greater uncertainty. So we avoid that. So that is very, very careful in selecting this, and cannot overemphasize how important in fact getting these proper samples and for training.
Okay, if I could ask regarding uncertainty, you talked about errors of omission and commission, and related that to rain-fed and not rain-fed. I didn't quite understand that. Could you explain what you mean by errors of omission?
Omissions, okay. This is how it works. When you produce a map, you call it as what you call producer accuracy. Suppose you get 88% producer accuracy. That means there is an omission of 12%. That means cropland, which was supposed to be mapped 100%, we mapped 80%, we captured 88% of the cropland. 12% we are missing. But at the same time, if the user accuracy is say 90%, that means there is a 10% commission errors, that means that are not cropland is coming into cropland. So both times it happens. So you have to balance between, optimize between having less commission or less omissions and less commissions and more less, both less. Yeah. Yeah. Okay.
Have you noticed any issues with bias problems with the machine learning and classification?
Yeah, in the sense, greater the ignorance, greater the bias. But that in the sense, suppose somebody, so you have to be a trained expert in the subject matter. That's all I'm saying. So suppose if I am asked to work on, say, medical science, and I know very little, and I try to do a classification, I can commit a lot of errors because in the sampling, understanding of the data and all that. So that is the biggest, what you call, even within the remote sensing scientist, if you are not a subject matter expert of, say, agriculture or water, you may not understand the whole background about, for example, species and cultivars and irrigation and nitrogen application, all these things come into factor. So you need to understand. For example, I'll give you an example. Corn crop in, say, Midwest has a greater biomass. Soybean has a less biomass. But in remote sensing, soybeans has greater NDVI compared to corn. That is because it's a nitrogen fixation crop. So just an NDVI, higher NDVI is not higher biomass. So this kind of understanding of the knowledge base of the particular subject matter, and there are other ways of getting, so you have to be careful, of course, user bias and all those. Yeah. Any more questions? Okay, we might have some time at the end to ask questions, or will be available. We'll give it to our friend from University of. Yeah, go ahead. Yeah, you want to use that? Yeah. Yeah.
Thanks.
Thank you.
Good morning, everyone. Today I will discuss about these two simple models for irrigation scheduling. One is Irrigation, another one is Irrigation Prism. This one is a web-based tool. This Irrigation, in this Irrigation, like we use observe weather station data, and this Irrigation Prism, like we use graded climate data. Main difference is weather data, everything is similar. This is very brief background. What is irrigation scheduling? We all know what is irrigation scheduling, and there are different methods of irrigation scheduling, like soil-based, weather-based, plant-based, and combination of this soil-based. One or two or more these approaches we can also use for irrigation scheduling. This figure summarizes like how methods used in detecting when to irrigate. This one in the US, based on the USDA 2014 and 2019 data. if you see in this figure, like very few percentage, like just about 6%, they are using the soil moisture sensing devices, and about 1% plant moisture sensing device, about 3 to 4% reports on daily crop water evapotranspiration, and computer simulation models very few, like 0.4%. So in terms of use of soil moisture sensor, plant sensing, then that evapotranspiration weather based, very, if you say in this total percentage is very low. Like that Irrigation, that one is just applicable for Texas, and then in Texas, like if you see in this table, like you can see many other tools already there. Most of these tools now currently not available. And if you see here, like area covered, like most of these for specific region, like some in Texas High Plains, some in Coastal Plains, some in selected different cities. And if you see also crops, like some just applicable to certain crops, like some cotton, some just for grass, and some for very few crops. And like all these are weather based, so no use of soil data. And then these are based on weather station data, and then no use of forecasted weather data. So what will happen in next 5 days, we don't know from using these tools. And then like these tools, they have their own weather network, and there is no integration of weather data from different weather networks. So like to eliminate some of those limitations, we developed this Irrigation, like that integrates weather data from different weather networks, and it also uses site-specific soil data. As I already mentioned, like this Irrigation based on observed weather data, and then this Irrigation Prism, like this one is based on graded climate data. Graded climate data, this parameter elevation regression on independent slopes model Prism data, that one is 4 kilometer by 4 kilometer grid, or 800 meter by 800 meter grid. By using that graded climate data, we just modify this application, just changing weather data. Like in this Irrigation, like we have weather data from these weather networks in Texas. And then, like in this case, we have enough data for calculating reference evapotranspiration based on a Penman-Mortet equation. But in this case, this Irrigation Prism, like we use this Prism climate, graded climate data. In this case, we have this minimum temperature, maximum temperature, rainfall. And based on this minimum temperature and maximum temperature, we calculated our reference evapotranspiration based on this Hargreaves-Sumner equation. In this case, Penman-Mortet equation. So you can reference evapotranspiration using different equations. Then soil data. This one is from Web Soil Survey, like this Surrogate Soil database. Based on user-selected field, we send that latitude longitude coordinate to that NRCS web server, and then we collect data for that particular field, and then we use that soil data. And then we listed some crop data for different crops, crop development dates, crop coefficients, root depths for selected crops. And for forecasted weather data, like we use this National Weather Service for next 5 days, minimum temperature, maximum temperature, and based on location of that field, we also calculated like forecasted reference evapotranspiration and rainfall. Based on that, when we calculate irrigation requirement in the next few days. And these are the list of weather stations included in this application. This is web application. And we also installed a few weather stations with collaboration with Texas Water Development Board. This one is very simple tool. Like as we know, water content in the soil, we can define like saturated once all the pore space is filled by water, that is saturated soil. And after draining that some of water by gravitational force, then the remaining water, that is fill capacity. And if there is no rain, evapotranspiration, plant water uptake, then at certain stage, the plant cannot extract water. At that stage, we call this permanent wilting point. And the water between this fill capacity and permanent wilting point, we call this available water. And between this available water also, we define this management allowable depletion. If the water content is above this, then we say like plant will get enough water. If water content is below this management allowable depletion, then plant will underwater stress. So our intention in irrigation scheduling is to keep water content in the soil within this range. Once the water content is close to this management allowable depletion, then we need to irrigate. And then crop evapotranspiration, also we use that coefficient to reduce the crop evapotranspiration. As I mentioned, like this one has data for some selected crops, crop root zone, then this crop coefficients, and then we calculate this reference evapotranspiration, and then based on this crop coefficient, we calculate crop evapotranspiration. If that one is below that management allowable depletion, then we use that stress coefficient for reduction. And this one is general flowchart of this application. As I already mentioned, like the main difference between this IRRIGWISE and IRRIGWISE Prism, just weather data. Like in IRRIGWISE, this one is based on observed data in different weather networks. And then IRRIGWISE Prism, that is gridded climate data from this Prism. And then we have this soil database from this surrogate soil database. Then weather data from this forecasted weather data from National Weather Service. Like from here, like near real-time reference evapotranspiration, rainfall, the soil data, then forecasted estimated reference evapotranspiration and rainfall, and then based on user input, like where is that field, what the crop is growing, and then what crop they selected, crop data, and based on that one, like then we calculate daily water budget within the crop root depth. And based on that one, like as if the water content is close to that management allowable depletion, we need to irrigate. If that one is above that, we don't need to irrigate. Then based on that calculation, we can see like, do we need to irrigate or no? If we need to irrigate, how much we need to irrigate, we can calculate. And then based on this tool, like we also developed one Android app. Like this one, we call this weather and soil. Like that, based on by using this application, we can get like hourly and daily weather data, including evapotranspiration, reference evapotranspiration. And I think I have another slide here. Yes, this is the this app. Hourly and daily weather data. We also calculate reference evapotranspiration based on minimum and maximum temperature. Then rainfall also in terms of inch, and then we have soil data for different horizons, field capacity, permanent holding point, soil texture, all those information user can get for their field. And this is basic some details of this application here, like similar to any application, user has to create their account, and then this is the different tabs in the field, like weather stations included in the app. And then if users just want to know the forecasted weather data for their field, reference evapotranspiration in next few days, or rainfall in next few days for their particular field, they can source and they can find this one. And then if they are growing certain crops, then they can add their field. Their field, what is field name, in which year they are growing, weather network, weather station, soil type. If they know all this information, they can select directly. If they don't know, like there is Google Map option, they can go to Google Map, and then they can search their field, they can locate their field. If one just clicked, and then it collects soil data from that web soil survey for different horizons. And then it also identifies the nearest weather station based on available database. Like in this case, the weather station is this one, and network is this one, and then this is 5.2 miles away from this field. Then the user can add their crop, and based on crop, there's crop data populated, and then if user has more detailed information, they can change those data. This is also crop-related data. Then soil data, this one is extracted from that web soil survey based on that user field location. And once user add that field, this is the field data stored in that application. It shows like our daily water deposit computation within the root depth from the planting date to today's date based on observed data, and from today's date, from previous day, like from today's to next 5 days based on forecasted data. And this one we can also see in the graphical report. This one is graphical here. Like these dots are rainfall, and this line is field capacity, and this one is permanent wilting point, and this one is management allowable depression, and this one is variation of the soil moisture within that plant root depth. You can see here, like this one is without irrigation. So in this particular day, 12th July, this one is below this management allowable depression. So plant will under water stress from this date. And this particular line, this one is particular when I capture the screen, that particular day. And as I mentioned, like these calculations are based on observed weather data, and this one is based on forecasted weather data. There is no rain, so the moisture content will still continue decrease. This one is without irrigation. Like if we continue monitoring this one, and once we are close to this management allowable depression, and that particular day we can irrigate. Like if we irrigate in this July 12, for example, 3.5 inches, and then we can increase soil moisture content to field capacity level. Like how much we need to irrigate, like that one we can based on the current moisture content and the field capacity. The difference between that two, like we apply that amount of irrigation. If we apply more than that one, then that will be more than field capacity, and that will be lost as a runoff. So we just apply difference between this current moisture content and this field capacity. Like once we apply irrigation, you can say the moisture content is here now, and then after 5 days, the moisture content will still continue to decrease. There is no rain forecasted. And then user can also subscribe for daily update, like for do we need to irrigate or no, based on observed data yesterday, and today based on forecasted data, like do we need to irrigate or no. This information user can get. This is summary. Like these are two simple web applications for irrigation scheduling. And for validation, like we did some field experiment in our university farm, and for corn, we did like we need to do more validation in different locations for different crops. That is still remaining. Like all these tools, like we hosted in this one this website, Irrigwise Present, this weather and soil. And we have also another, this iWait. This one is irrigation water estimator for Texas. And that one is based on historical climate data. If someone wants to grow certain crops in certain location, then how much water we need for planting purpose, like this, based on historical climate data. And the same application, this iMansys model, like this one is desktop, like based. And in this case, also by using historical climate data, we can calculate like how much irrigation water we need for particular crops at any location. If we have soil data and climate data, like we need climate data, crop data, irrigation system, and then soil data, then water loss, those per runoff, and interception, and then we can calculate irrigation water requirement plus different water deposit components for historical climate data. And like by using the same tools, like we did one study by using both historical and projected climate data. Like if we grow certain crops in urban area in US, in these locations, 8 different locations, how the water requirement will change. We use like turf grass, spinach, sweet corn, and carrots in all these 8 different locations, and how based on historical climate data, how much water required, and based on projected climate data in 2040 to 50, how much water we did analysis for this particular paper. If you are interested, you can check this paper. That's all from my side, like this acknowledgement for USDA and okay, that's all. Any questions? Yes.
Thank you for this very interesting presentation. Maybe I missed the information, but how is crop evapotranspiration calculated? According to which formula?
Like for that weather-based irrig-wise, we use Penman-Monteith equation.
Penman-Monteith.
But for that gridded climate, in that case, we use Hargreaves-Samani equation.
So you use in KC as well, in the Penman-Monteith.
Reference evapotranspiration, then times KC, crop coefficient, then crop evapotranspiration.
Okay, and so you are, of course, taking into account different areas, different KC for different areas.
We have default values just for one values, but user can change those values for that particular area.
So the user can input different
Yes.
KC according to his area?
Yes.
Okay, thank you.
Thanks.
Any more questions?
Sorry.
I wanted to find out, was there any reason why you use Hargreaves for the second two?
Sorry.
I mean, the ET equation you use, I mean, for the second one, you mentioned that you use Hargreaves.
Yes,
Calculate
the
the ET.
main reason for that one is like for Penman-Monteith equation, like we need wind speed, then solar radiation, more parameters. But in that gridded climate data, we have just minimum temperature and maximum temperature. Based on that one, we calculated. If we use Hargreaves-Samani equation, like we just by using minimum and maximum temperature and location of that area, we can calculate reference evapotranspiration.
So the other weather parameters were not available? Was
In that gridded climate data, the one we can use for reference evapotranspiration, all data are not there.
Okay. Okay, thank you.
Sorry, another question. Are you also taking into account useful rainfall? Because as I see, the first approach is based on forecast, weather forecast, and that is also considering rainfall. Is the system considering useful rainfall as well, in the second and the first approach? Because as we know, not all of the rainfall that falls
Yes,
is
effective rainfall.
available or useful for.
Yes.
You have to take that into account when you're planning for irrigation scheduling and so on.
Like we use effective rainfall without considering that runoff and deep drainage.
So you're taking into account, of course, effective rainfall when
Yes.
you're applying this. Okay.
Any other questions? If no, we can.
Thank you very much for that presentation. I was just wondering, do you have any maybe statistics on how people are using, producers specifically using the apps? Has it gone beyond, let's say, the research spheres, maybe to producers, and how are they applying it? Yeah.
I think we need more validation if we can validate in different locations for different crops, and like for now they can test, but if we can do some validation, it will be more useful.
Thank you so much for that presentation. So I'm just wondering, have you tried to compare this tool with other, scheduling methods like soil moisture sensors and all other methods?
Yes.
In terms of, water savings and also yield differences. Thank you. So this tool is for irrigation scheduling, right?
Yes, yeah.
But there are different tools that producers are using, such as soil moisture sensors, or other satellite-based ET scheduling. Have you tried to compare this tool with other tools that are being used out there?
Like as we already in the beginning, I said like these are very simple tools. Weather-based tools are very simple tool. Like if you use more like soil moisture by using different soil moisture sensor, if you monitor soil moisture, that will be more accurate. And if you use plant sensing, if you can combine plant sensing and soil moisture, that will be, I think, more reasonable. But this weather-based, this one is less accurate. But cheaper. Yeah, thanks.
Thank you, Ripendra. Good morning, everyone. So my name is Davie, Kadyampakeni. I work at the University of Florida, and my area is a little bit focusing on soil and water management. Mostly horticultural crops, so a little bit different from the Midwestern regions of corn, soybean, and others. So I hope this provides a little bit of a blend of what Dr. Prasad was talking about plantations. So that's exactly what I work on. Citrus, blueberries, bamboo, and others. A few horticultural crops like vegetables. So I'll show highlights, a little bit of the applications apps that are relevant for Florida, like what Dr. Awal was talking about for Texas. Then I'll show a few applications of how we use that in the field. So sorry for colleagues that are working also in the developing countries, because here I think it's a bit of a blend. So I work mostly with commercial growers, 1,000-acre plantings. But I think some of those can be tweaked for developing regions, assuming you have enough resources. So I want to really focus on the computer programs that we use, very heavy modeling. For example, we have what we call the Florida Automated Weather Network. We have more than 96 stations in Florida, where we use those weather stations to predict the irrigation needs of our commercial farmers. So mostly using field capacity, spacing of the planting, and also irrigation specifications. And that app is for crops like citrus, vegetables like tomatoes, and leafy vegetables like lettuce. And then also blueberries, you have peach, you do have cotton in there, and also you have peanut. So that is, I think, the top one that I love. But there are several others, including using personal computers, whereby commercial growers, some people say, oh, we don't want to use apps, we want to use data in a computer. They can have all the parameters for the soil that they're dealing with, and then put that in a computer model, and then it stores all the irrigation data, and then they print reports for the irrigation needs for their farm. Now, more recently, in a collaboration between faculty in my department and those of the agriculture and biological systems engineering, we have come up with smartphone apps. So those of you have like iPhone or Android, you can use real-time data. So a farmer can be on the beach enjoying, having a good time with their family. But so go ahead and schedule the irrigation and be able to save some water. So just instead of all the time going to crank the pump or turn it on, that can all be automated using the smartphone apps. And they can also get notifications about the probability of rainfall. So you can shut down your irrigation just based on the fact that you can forecast all that irrigation needs of your farm. So to begin with, I would like to show you a little bit about the Florida Automated Weather Network. I wish I had a little video, but I wasn't sure about how that is going to work. I should have asked maybe, because I could have shown step by step, but still I'll try to go through that right now. So as I said, we do have over 96 weather stations in the state of Florida. But this is where I'm located, so I'm biased to pick the center where I'm at. But within Florida, we have about 96 of these centers. And then you can choose whether you want daily summary of your weather data, or you want to get and the data of your interest, or you want to get weekly summary, or monthly summary, and all that. And then you have information on the temperature, rainfall, solar radiation, evapotranspiration, and then the hours of interest, and then also you can have different temperature ranges. One thing I want to mention is that I think there was a question in the audience regarding the model for estimating the evapotranspiration and so forth. So in Florida, we have kind of modified the Penman-Monteith equation to suit our needs, because there are some parameters in there that are a little bit global, but not fitting this, the parameters that we need for Florida. So the model is kind of reconfigured to fit what we have for Florida sometime in 1984. So we use the Penman-Monteith model, so we can't really take credit, but now we have adjusted it and come up with steps for using it for our conditions. And then, if you're in there, you can pick the crop you're dealing with. So you can do citrus, vegetables, strawberries, and other row crops like corn, or cotton and others, or tough grass. So in this case, let me pick an example of citrus as a crop, because that's what I primarily work on. And then you notice that you need to put between row spacing between the plants, the in-row spacing, and then the diameter of the emitter, the wetting diameter, and then the rate of irrigation, which is like in gallons per hour, or the pattern. So you might have, here I put 360 degrees, but you might have 270 degrees, you might have 180 degrees, you might have 90 degrees, depending on the size of the plant. If you just plant them, they're so little, just about 50 centimeters tall, you might have to use a different wetting pattern. If they're a little bit 2 years old, you might have to increase that to somewhere around 180 degrees. But this is for a mature planting, so you want to wet the whole rooting zone. The system efficiency, usually, we really don't go to 100%, so we assume there'll be some inefficiencies, but 85% is a little bit reasonable. 90 is even ideal for micro sprinkler irrigation. And then you have to pick the type of soil you are dealing with. So that was, I think, Dr. Awal was talking about using SUGRO for the determining the soil type. In Florida, we also use the same one. We have all these soil types that we have in the state. So for this one, I picked Apopka, and then you have to pick the irrigation depth. So here it says 36, but I mean, you can go as deep, as shallow as 12 or 10 or 6. And then the irrigation trigger depth will be the active root zone. So for citrus, you want to look at the top 15 centimeters or 6 inches in this case. And then you pick the phone station you're dealing with. So in this case, I started with Lake Alfred. Now, if you put some selected variables that are put in there, and then you ask the app to execute that, after you put all those inputs, for example, here, I put some spacings and all those variables, and then you let the model create a schedule for you for the next 2 weeks. Then it will give you something similar to this. It will give you, the time like for 4 days, it will get for 3 hours or a minute. And in this case, you're looking at areas that are about 100 acres or thereabouts. And then it says if it rains less than 1/4 of an inch, make sure you irrigate. If you get at least 1/4 to 1/2 of an inch or greater, then you can either delay by 2 days or delay by 4 days. So then you can make those decisions. And this is all very helpful to our commercial growers. So as I should indicate that here, you have that information. So you have information on evapotranspiration from the model generated, and then also you have information on the rainfall. Now, the other one that we have kind of modified based on the Florida Automated Weather Network, then we use what we call the Florida Department of Ag and Consumer Services, and then the IFAS, Institute of Food and Agricultural Sciences, combined program for helping growers. Because some growers say, oh, if you use your weather stations, that's so pricey, they're not easy to use. So can you give us weather stations that we can put in our farms? So we do have what we call cost share programs where farmers can use real-time data for frost protection and irrigation scheduling. So in the months of December through March, when you can get freezing temperatures, freezing in cost, because I think freezing will be, if I say 30 degrees is freezing here, everyone will say, oh, look at you, that's not even snowing at all. Yeah, so in Florida, that's a big deal. Yeah, so 30 degrees will be like, wow, everybody's in jackets and trying to watch for cold weather, and warnings from schools, or warnings from work that please stay warm and don't let yourselves be frozen to death. Yeah, so that's 32 degrees and 30 degrees. Once you start getting those below temperatures, we try to use those weather stations for frost protection. So that's why we have those for our commercial farmers. Now, in terms of smartphone apps, as I said earlier, so these ones work for the iPhone or Android, and then they still use the Florida Automated Weather Network, but now these ones are a little bit more handy to our commercial growers who don't want to waste time sitting on a computer trying to put in data, trying to put in weather variables. As long as they have a crop of interest, either citrus or strawberry or turf or any other row crops, including vegetables, then they can use these apps. You can download them. If you just put in the Google store, you put Smart Irrigation app, you can download that and then pick the crop of your interest. And then you can use this for scheduling irrigation for the next 2 weeks, a week, or a month. So it helps with planning, real-time planning for most of our growers. And you can be on a vacation in Europe or on a vacation in South America and still be able to schedule irrigation. Isn't that interesting? Yeah, so then I would like to talk a little bit about some of the tools we use for measuring the soil moisture content, because I think we can use all those apps, but we have always asked growers to use some soil moisture sensors to be able to track the water usage and storage. So in this case here, bear with me, I'm a little bit biased because I know we have all these kinds of sensors commercially available. But in Florida, for some reason, these areas where I normally work, we have very dense and very sandy soils that are about 95% sand. It's very difficult to control the irrigation and very difficult to retain water. So we normally use the capacitance probes, like these ones, or the acclimate sensors. And there are those that are handheld, but we recommend those for growers, like where you put the probe in the ground and they get a reading right there, because some growers don't want to have those connected to a data logger. But we recommend having these kinds of sensors if a grower really wants to have robust data and tracking water use by depth and over time. So these are some of the tools we use. And in other cases, we use the bigger probes that can go all the way to a meter depth to make sure they can, if they want to look at salinity or temperature and soil moisture at the same time, some of these probes can capture that. So we encourage our growers to use these kinds of sensors that are usually provided by some of these companies. And what we have learned, and I think those conditions might vary with other states, but in Florida, we have not had good success recently with mostly tensiometers and granular matrix kinds of sensors because of the low level of accuracy or the need for maintenance in our sandy soils, because we have very poor contact. So I've had so many studies, and then we come up with this little table that gives us some guidelines on what to use. So usually for our growers, we recommend using capacitance probes, time domain transmission, or time domain reflectometry. That's what works for us. And then if we really don't want just to focus on the soil, but we want to use plant-based sensors, then we use some of the, let me see, oh, excuse me. We use some of the chemical kind of scientific data loggers where we put sensors on the plant, and then we track the transpiration of the plant over time. But these ones are made for us to kind of calibrate the response of the plant in 2-week intervals. So we don't do this continuously. The companies always tell us, oh, you can do that throughout the year. But we have tested and realized, oh, you can kill the plant. So we do this for 2-week intervals, maybe 2-week interval in spring, 2-week intervals in summer, and 2-week intervals in fall. And then we can determine the optimal thresholds for irrigation scheduling, especially the deficit irrigation. Now, in other cases, I've also tried to use weighing lysimeters, where we put scales under the taps to actually determine the crop coefficients for different types of varieties of crops with different disease conditions. So some of those tools I've used to come up with those variables. Now, in other cases, I've also tried to sketch irrigation using dendrometers. These are put on the trunk of the plant, and then they let you know during the day, in the morning, afternoon, or evening, when you have changes in trunk size and changes in water use. So these have been very helpful for us in terms of irrigation scheduling. This other on the right is where we have been using the pressure bombs to determine stem water potential and see when the trees are water stressed or not. So how do you use some of these tools in action? So one example I have for you right here is where we had this work done on comparing two levels of irrigation. So full irrigation at 100% of crop evapotranspiration, and then the deficit irrigation at 66% evapotranspiration on tomatoes done in the spring months when it's a little bit cold, from January to somewhere in April. And then in fall, that is somewhere around August to December. And one thing we noticed was that when you begin the study, so you still have a little bit of the high reference evapotranspiration, but the crop water use is a little bit lower. And then as the season progresses and the plant starts maturing, you tend to see a higher level of water usage with a higher level of irrigation. And then, of course, the deficit irrigation treatment shows a little bit lower level of water needs. So one thing we noticed, I didn't show the yield data, I just had this graph for this production, but one thing I noticed was that even the yield was not compromised. So something to think about, that we could lower the irrigation needs for tomatoes, because this was done for over 4 years by our PhD student, Timothy Yankojo. Yeah, and then in the fall, you can see a similar pattern, high reference of evapotranspiration at the beginning, but now as the season progresses, the higher irrigation rate tends to use a little bit more water compared to the deficit irrigation treatment. So a little bit something to consider, especially for most of these commercial plantings, whereby if you save like 1 million liters in a season, that's a big deal. You reduce the cost of irrigation by the commercial grower. So another one, so you see a little bit heavy detail here. Another study where we were looking at use of different irrigation rates on commercial oranges called Valencia variety. And we had a rooster called US 897 developed by USDA. So we had 2 to 3 rows of planting, and then we were comparing in the first years 2 levels of irrigation. So 2% of the ET and 100%. Then in the second year, we kind of modified a little bit to use actually lower rates of the ET, so 26, 40, 53, and 81%. And then, as you can see, so these are some of the densities. So a little bit, here's the 12 of the higher density, here's a bit, here's the higher density, here's a bit wider, and they're made on slightly bigger beds. So the aim of this study was to determine the amount of water required to grow young trees at higher densities, because that was not known in Florida. Most of the growers use very low densities, and they just keep wasting water. So these are the 3 densities from 181 trees to all the way to 363 trees per acre that we were evaluating. So one thing that we learned in that study was that in the first year and even in the second year, you notice that the higher level of evapotranspiration, 100% ET, was always, you are putting a little bit more water compared to the lower level. So obviously, you are wasting a little bit more water because we didn't see any water stress. I'll show some of those data in a minute, even in terms of nutrient use efficiency. Now in the following year, we kind of tweaked and then provided a little bit more deficit irrigation at 81%, 53%, 40.5%, and 25.6% of the ET. And one thing we noticed was that all these didn't require as much water as the 100% ET in the second year. So we can lower the irrigation. Now I'll show in the next few slides the impact of these rates on the responses of the plant. So as you can see here, sorry, it's kind of a heavy table, but I still want to show a little bit of what we observed. So as you can see, at each level, using the ETO blended credo model, we found that the crop coefficients were increasing with the planting density. So at the higher density, you tend to get higher levels of the crop coefficients. At the lower density, you get the lowest levels of the crop coefficients. So obviously, you have to scale down the amounts of water you put. The fewer the plants, the less of the water required. The more the plants, the more the water required to irrigate. And then we also try to look at just the level of nutrient accumulation in the plant. So as you can see in the top level here, we have macronutrients, nitrogen, calcium, potassium, magnesium, and phosphorus. And in the bottom graph here, we have iron, manganese, zinc, boron, and copper. So one thing we noticed was that you are getting higher accumulation of nutrients for the macronutrients with the highest level of irrigation. Though we didn't see any differences in treatments except for nitrogen, but we noticed that maybe it would be probably ideal to stick with the 53 or 81% of the evapotranspiration needs. For the macronutrients, we noticed that mostly it was the 100% ET that resulted in better uptake of the macronutrients except for boron and copper. Now, in terms of the soil moisture retention and storage, we noticed that the higher levels of irrigation in 2018 were always ascribed to the higher level of ET. So 100% resulted in a greater level of soil moisture. Here, I just messed up my scale, so this should have been up there. So this is at 1% ET, so a little bit of elevated moisture content in the soil. So you notice that the other 51%, 53%, and then 40% or 26% started providing a little bit lower moisture content in the root zone. So maybe something to consider and think about when you are looking at using these deficit irrigation practices. Now, when it comes to the stem water potential, which is an indicator of the stress, we noticed that most of the plants that were watered at 26 and 40% resulted in a little bit of more stress. So we are considering not really imposing very low stresses in citrus. We might have to stick with 53% or 81% in that area to make sure we don't have much water stress. So another example that I have for you is another study that we did under greenhouse conditions where we compared two levels of irrigation, 80% ET versus 100%. And then we had two conditions of the plants. For those of you who know about citrus in Florida, and actually across the globe at this point, we do have what we call citrus greening disease, which has actually limited the scope of production. So this disease has, in Florida, for example, led to the reduction in production area by about 50% at this point, since 2004. Yeah, so one of the major impacts of that disease is to limit the root growth of the plant and also resulting in a lot of severe defoliation. So we have been conducting some of these studies to try to understand the impact of irrigation rates on that dynamic of limited root zone, because there will be limited water uptake, and then defoliation, which will be limited for synthetic capacity. So how do you improve the irrigation scheduling for those kinds of plants? So one thing we have noticed is that, so as you can see in this study, a little bit, it was just a 2-year study, so starting from August all the way to around October 2021. So one thing we noticed was that we saw some differences in stem water potential between treatments. So one thing that came out was that this should have been a negative because all these are negative values. So we found that the stem water potential ranged from negative 2.4 to negative 0.6 megapascals. So one thing you notice, especially in May 2020, we were noticing that the trees that were like this one, the striped, and then the black ones, these are the ones really impacted by HOB. But it seems that when you still irrigate the HOB affected plants at the normal level of irrigation, then you reduce the stress a little bit. But when you put the deficit, we notice that you get a little bit of water stress in the plant. And then one thing also noticed was that, for example, in summer 2021, you notice a little bit of stress in the healthy plants NHOB, the healthy plants at the lowest level there. But very interesting here, we also saw some stress in the healthy, the HOB plants that were irrigated at 100% of the evapotranspiration. So kind of confusing, but some of things to consider. So one thing we are learning is that somehow at 80% evapotranspiration, we still can manage, like for example, if you notice here in the other seasons, August 2019, October 2019, or March 2020, we really didn't see much difference between 100% ET or 80% ET for similar conditions of plants. So somehow, that's something that we have learned that we might be able to get away with it if you lower the irrigation rate. And then, excuse me, so this kind of let me down when I was transferring from my template to this template, so my apologies. I think that's a similar graph, trying to show one more slide. And then we use some of the plant-based subflow sensors to track the water use daily. And one thing we noticed, so you notice this is for 2020, spring 2021, and summer 2021. Excuse me, let me start here. One thing we noticed was that most of the water use was occurring between 8 o'clock to somewhere around 8 p.m. And one thing we also noticed was that the peak transpiration was always between 12 o'clock to somewhere around 3 p.m. So something to consider when you're scheduling the irrigation, that maybe that's a time which to optimize our water applications. And then, of course, one thing we also noticed was that trees that were irrigated at 80% ET had at least 30% greater subflow than those that were irrigated at 100% ET in fall 2021. But now we noticed that in spring 2021, trees under 80% ET showed 28% greater subflow than those under 100% ET. So somehow, the trees that were irrigated with deficit irrigation tended to survive, that I'll use more water to sell business. Yeah, so something to think about, that maybe if you limit the water application, that's going to trigger more water use in the plants. So here we are. What's the take-home message from all these slides? So I say, okay, look, we have the tools available for irrigation management, using sensors, using apps. We can optimize water management. We can optimize water savings. And then, of course, we can also use all those tools both in commercial settings but also in academic settings to try to demonstrate how much water to save in the commercial cropping systems. And then another take-home is that for sandy soils, you really need to optimize your irrigation management by using sensors, by using irrigation apps, and so forth. So at this point, I'd like to thank most of my collaborators, mostly from Florida, and also our sponsors. And I'll be happy to take any questions you might have. Thank you.
Thank you, Dave, for that presentation. So I was just wondering, have you tried to couple two methods to see if you can be able to improve the water use efficiency in trees? Let's say if you monitor subflow with soil moisture, how could that work out? Have you tried to look into those, ideas?
Oh yeah, we have tried, excuse me, but unfortunately, we haven't found a good correlation between the soil moisture and the subflow. So I tried to do that multiple times, I think for like 8 years, and different setup of experiments. Yeah, but that's still work in progress. Yeah, but we have tried, but we noticed that somehow soil moisture dynamic is a bit different. We tend to see cycles going by the irrigation levels in the soil, but the subflow tends to be diurnal, so it will start peaking somewhere around 7 in the morning, then peaks throughout like at 10 a.m., then it starts going down somewhere around 4 p.m. Yeah, so that is something that I think either we have to get a little bit more help from statisticians and a little bit of that, because I think it's a bit of nonlinear regression and least squares methods that they have to help us with to calibrate those ups. Yeah, but that's a valid question. Very good.
Thank you.
Yeah.
Thank you. A related question. Did you see or did you look at growth increment of the trees or the yield of fruit of the trees based on reduced irrigation compared to 100% of ET irrigation?
Good question. My apologies, I didn't include the data. For this study, the one where I was showing those rates, they were very young trees, so 2 to 3 years old, non-bearing. But in another study that I published, but I didn't share here, we looked at the yield, but there we didn't lower irrigation. We used the same irrigation rate, but varied the irrigation schedule. So irrigating every 2 days, or irrigating every day, or irrigating twice a day. Yeah, in that study, we didn't see any differences in yield. Yeah, but for the other one, we are yet to start getting yield. We'll try to generate that. Very good point, because commercial growers tell us if we can't show yield, those data are useless. Yeah, so valid point. Thank you. Thank you.